So I will give kind of an overview talk today about what we are doing here at Fraunhofer in terms of using geostatistics and offshore wind farm ground modeling. There we have worked closely together also with geovariances, with Petram. And there are many actually authors to be named here. This is just the main ones here. This is a lot of the work of many people actually. And it was all planned a bit differently. So originally my student should also give a talk, but he cannot participate today. That's why I've merged now basically different presentations. And yeah, we will have a bit of a longer discussion on that. Just quickly to for Fraunhofer, maybe just one slide to make you aware of what we are, because we are basically part of the Fraunhofer Research Society, which is, I think, the largest research society in Europe, or at least in Germany. And we're based here in Bremen. As said already before, we are the Institute for Wind Energy Systems, which is basically a branch institute dealing with all kind of things related to offshore wind, and also now, since a couple of years, more in the direction of hydrogen. But here we're talking about the assessment of soil conditions. So was there something? Sorry, I heard something. Oh, good. Okay. Yeah, so this is where we are working in. And now, since I think that we have some people which are not familiar with offshore wind farm development, I wanted to give a quick overview about what we are talking about to make things a bit more understandable later. So in offshore wind farm development, we're working with different kind of data. We're talking here about 2D or 3D seismic data, marine seismic data in this case. We're talking about specific site investigations, which can be object detection or, I don't know, site-scale bathymetry. I will not talk about this today. We have, of course, also bore data, and at the end of the day, column penetration testing data, which is the focus also on our work here, together with seismic data. And this data needs to be basically integrated in what we call nowadays an integrated ground model, which contains all sources of information. In this case, here particularly, we are focused on the creation of what we call interpolated or synthetic CPTs, which is basically a prediction of CPTs apart from actually investigated locations. But we come to that later. We also have geotechnical laboratory data normally, of course, which plays also a huge role, which will not be focused on this work here. And then at the end of the day, what we want to do, specifically also at IWES, create site-specific geotechnical parameters, because they are interesting for the design of monopile foundations, or in general foundations of offshore wind turbines, as you can see here. So we are, at the end of the day, this is the final product, right? And as geologists or geophysicists, it's our job to characterize the subsurface for building those turbines. And this is the data, again, we're working with, just some simple figures. So marine ultra high resolution seismic data. So we're normally going out with a vessel, acquiring the data on a geophysical way. 2D mainly is the main focus in the industry right now, but there are more people going in the direction of 3D seismic data acquisition. But whatever you see here in this presentation will be 2D seismic data. We have the geotechnical data. This is now a CPT being derived. And as you can see, always a bit complicated because we always need a vessel. This is why it's also time consuming and very costly, which is why we want to actually reduce the necessary amount of site investigation, for example, by using synthetic CPTs. This is just an example of an offshore wind farm area from the Dutch sector, Dutch North Sea here in this case. I just picked this one here because you can nicely see what we're talking about. So what you see in gray is the line spacing of the geophysical data. So normally we derive the geophysical data by going with a vessel across the wind farm area and measuring everything in both directions here, basically, which, of course, when you acquire 2D data, leads to gaps between those 2D data, which is why we need to kind of quantify the uncertainties within that, which is also something you will see later, but it's important to understand, I think. And the points here are basically CPTs or other kind of geotechnical data being distributed all over the area. But as you can see, we have, limited amount of geotechnical data, but basically the whole area covered with geophysical data. And we can make use of that by integrating then the geotechnical and geophysical data, also in a data-driven and quantitative way, as we also see later in the presentation. And this is normally kind of, well, more or less a final product, right? So we have a ground model kind of. This is just an example from a German wind farm area here. We have technical data integrated. You can see here just some main units and also problems we are dealing with. So here the yellow horizon is basically a tunnel valley. You will also see some pictures of that later, but we need to kind of characterize that. As you can see again here for the foundations of the wind turbines, to avoid geohazards, because those channels, for example, can be geohazards at the end of the day. So coming to the first example, probabilistic ground modeling. Why is this important? Because simply what I've said before is that between known locations, we're actually not quite sure where the horizon or the unit goes. So normally as a standard, this is not really quantified. So you have a best estimate of wherever the horizon lies in between, for example, the 2D seismic lines. But of course, this is just a single truth. So we're normally having this, what is called here mean model, but we want to quantify what is basically the range of possible solutions here. And that's so just different figures saying basically the same. So the here, for example, this is a kriging example. If you would just do the kriging here, you would have the best estimate between, but of course you have a variety of possible solutions. This is where the simulation, for example, is interesting for us because we have different equally possible solutions for one problem. And this is also the reason why we're performing, in this case, geostatistical simulation. Here's just some figures to pick you up. I think you're all well aware of the concepts here, but this is what we can produce from that. If we have different horizons, we can create those spaghetti plots, basically. We can create probabilities, but we also have a look at entropy, which I think is a nice concept. This is just a figure basically showing the concept behind the entropy, and you will get the highest entropy basically here in this example where you have the most different units basically within one potential cell or grid cell, whereas the lowest entropy will be wherever you are quite sure that there is just one unit, let's say it like that maybe. And this is just a rough example basically from our seismic data. It's a bit blurry here, but anyway, what I want to show you here is basically, as you can see here, that there's of course one horizon, a depth for one horizon for the model, but this is just when you have basically one velocity model. But what we're looking at is actually more like probabilistic velocity models, which give us different possible depth of the actual unit we are encountering, and we can make use of that basically and come up with a probabilistic ground model at the end of the day. And this then incorporated on true geophysical, true offshore wind farm data. You can see an example here. That's the N9 area of the German North Sea. And here in this case, a fixed depth uncertainty was applied to different horizons. And then at the end of the day, it was simulated all over the place, let's say it like that. So here on the smaller pictures, you can see basically this is a source of information that is the line spacing of the geophysical data. And but as you can see here, you basically have different units here with different possible solutions. On the lower units, you have basically, I mean, there's not much to happen, but what is of course interesting is the upper units here, where we have some valleys cutting into the different horizons, which makes it much more complex from a geological point of view. And then we can, of course, just classify the units, which we normally do, but then we can also say something about the probabilities and also basically look at the entropy. And those are the figures a bit larger, just the same. I mean, for the probability of the units, this is in this example, unit 4. It's not very interesting, to be honest. So you have very high probability within this package that it's this unit 4, which is quite clear, I would say. But you have decreasing probabilities at layer boundaries. Where it becomes interesting, I think, is with the entropy again, which is giving you the combined uncertainty quantification of the model. And here we have the different units acting as one or being visualized as one. And here, of course, it gets more interesting where basically different units cut each other. This is close up here. I have not put in the color scale here. It's just for the visualization. So high is red is high entropy and blue is low. But you see where the different horizons cut it in to this or intersected. Basically, you have the highest entropy, which is logical. But it's I think it's good to quantify such things or to give a more informed ground model to the end user at the end of the day. And this is just a visualization from on top of the wind farm area, let's say. And here you can also nicely see how it would look like for the uncertainty on a area-wide picture, let's say. You can see in blue here clearly the line spacing of the geophysical data, where you are quite sure that you know what you encounter. And then apart from those lines, you have at least partly high uncertainties, depending on where you look at. So here you don't see a big difference, but here it becomes reddish, so high uncertainties in this case. And this is interesting because those are areas where we encounter actually channels or tunnel valleys. So we have steep flanks, we have varying morphology of the units, the reflectors, and this is why we get high uncertainties. And nice way to visualize, I think. Coming to the next example, another thing we have just investigated, and we're talking here about specifically the paleo channels we encounter in offshore wind parks, and we want to quantify this also in a probabilistic manner that also comes back to the probabilistic ground model idea, but we specifically focus here on the channels in itself. Just some, I think, very nice figures of what Europe and specifically the North Sea looked like in the past. So as you all know, we had some glaciations during the different glacial events. Here you see the nowadays boundary of the different countries. So here we have kind of Germany, here's Netherlands, and then we're coming to France here. And you see where I sit actually now, we had a couple of 100 meters of ice sheets above our heads a while ago, let's say like that. So we had glaciation events where we had different depositional systems, but we also had events where the basically the sea level was not as high as it is nowadays. So, and this led to the fact that the current or nowadays North Sea was actually land back then and had rivers flowing through it. And those events, of course, caused incisions of the geology and caused different depositional systems. And this is what we see nowadays when we're looking at in seismic data, where we have, for example, those tunnel valleys created by glacial events, for example, or also just, let's say, normal river channels created by, the paleo rivers, which are nowadays basically ending at the shoreline. But all of them are kind of geohazards because they can contain very heterogeneous material, and which can be a problem in when installing wind farm foundations. And actually, Piram brought us to the idea of applying multiple point statistics. So thanks again for that. And we looked into this for a while now. Actually, last week we submitted finally a paper on that. We see where it goes, but just as an information for you. We wanted to make use of multiple point statistics to create different realizations to come up with probability of the channels using training images. That's a concept you can basically see here. Here is the situation we have with our geophysical data. So this is basically the geophysical line spacing here. And we just basically took the interpretation from the channel. So wherever we have a channel, this is classified as there's a channel. And wherever we have no channel, there's no channel. And in between, we have unknown unknown data, as I've described before. And for now recreating the channels, we use MPS using training images, as you can see here. So this is actually the same channel system as seen here, but only visible on the geophysical lines. So this is also how we create basically our conditional data for the later calculations. We just take a training image and just pick up the information from the different lines. And using MPS, we can just scan then basically the training images, and wherever we fit the pattern of known data, we can copy paste the information into our simulation grid, to say it in a short way. And in terms of training images, we can use whatever we want actually. So I have some examples here. This and this one here is an example from true offshore wind farm areas. So you can see basically here some nice channel features, but you can also see that it's kind of hard to distinguish at some points, like here. We use those images to map out and at the end of the day channels. And as you can see in this example, this one here is also a very nice example. But theoretically, we can use everything we want. So we also work with some figures from the literature, actually. Or theoretically, this is just a snapshot here from Google Maps. Take any channel system you find and map it out and use it as training image. Because this, on land nowadays, I think it's actually France. This is the same as this one here, because this is formerly river channels, which are now submerged beneath other depositions. Yeah, and this is some of the examples. I have to admit, this is not the recent examples, but you will see some more advanced examples in the paper, which is hopefully going to be accepted at some point. But this is where we started with. So we have different training images. So this is a bit complex now here. So we have training image 1, we have training image 2 here, basically. Same area, different area says that here we have used the same conditional data and the same training image. And here we have used this conditional data from above, but a different training image, because we wanted to investigate different things. We wanted to investigate the sensitivity of the the selection of the training image, but also different things like the line spacing of the geophysical data, as you can see in this direction here, basically. And you can see now different line spacings indicated by the white lines here. So you see we get narrower when we go to the right. This is the actual line spacing we encounter for geophysical data in a standard offshore wind farm characterization. And here, this is kind of some numbers I saw in industry projects, 500 meters, and this is kind of artificial thing. So we wanted to see the other end member, how close can we get to have still a reliable result? And the answer is, of course, this is not reliable. So you see basically in red, you have high probability of encountering the channel. And this purple is low, is basically 0. Maybe going from right to left, it's better to say like that. So when we have a very dense line spacing, we can replicate the channels quite nicely using the different training images. It doesn't really matter if we use training image 1 or 2. You see that the results are quite, have a quite high confidence. Now it becomes, well, worse, let's say, with 500-meter line spacing here, although I would say that GI1 still works quite good, but you see with the different with the other training image, you get very disruptive channel appearance here, although still you can follow the channels. And it becomes very messy with 2,000 meters. I mean, because here you're starting to, where you see it here, you see it kind of in this area, develop channels which are actually not there. And this is, of course, dangerous if you want to use this effectively in ground modeling. Because the idea at the end of the day is to kind of quantify the position of channels better, apart from the seismic lines, to just basically de-risk installation processes, because you don't want to hit it with a foundation. And this is just a close-up of one area we made with the probability to the left and now the entropy to the right. It just gives you kind of same but different information, I would say. but you can see the different performance here for line spacing of 500 meters for the same training image, but then here also for the different training image, you see how it performs worse. The entropy is basically just giving, again, another kind of information with very certain being here this purple thing, and it kind of maps out the boundaries of your results, which is also, I think, very nice. Yeah, this is just not nice pictures here, but what we also investigated here basically is a comparison between multiple point statistics and sequential indicator simulation, because we wanted to compare that also to not training image based solution, but also to a variogram based solution. And I just put it in there again in the paper. There's more information on that, but here I just wanted to visualize that basically you can see that nicely. Here's MPS and here's SIS, that it works also quite well for dense line spacing, but you see this what I call kind of a halo here around the channels. It gives you a broader uncertainty range, which is neither good nor bad, I think, but it gives you a bit of another information. So you can see it basically, I talked about that maybe later, but here's coarser line spacing. This is also interesting because then SIS suddenly really doesn't perform anymore. You can see that here it becomes very disruptive. But for smaller line spacing, that's what is interesting. You can see it better here now, is that you have this, well, again, what I've called a kind of a halo, but you have a wider coverage of a probability that you might encounter a channel. And I think that is worth a lot because when we're talking about, again, design of monopiles, you want to be quite sure that you don't encounter a geohazard. And where MPS performed very well because it's very nice connectivity for channels and everything. It works very well for that. But it's also very sharp wherever we would encounter a channel. So here this dotted line is the true channel location, which we know from the gridded channels. And you see it actually always ends up there, and it doesn't really, goes across it. And sometimes it even doesn't cover it here, whereas the SIS is going beyond that. And I think for risk assessment, it might be a bit more favorable. Yeah, let's do that. And coming to last example, the predicted or synthetic CPTs. This is something I've specialized on since I've started at IWES. So that's I would say my core competence also, and something we have worked on the most so far. I'm coming back to my introductional overview and slide, basically showing the different steps where I have talked about also in offshore wind farm development. But now in this particular case study, we went also a bit further and used the information for the actual design of the monopile foundation, and to see what effect would have predicted data on the design process of the wind turbine. And I can just say that this is really something which interests the industry right now, and which is a huge discussion at the moment beyond people which deal with those kind of things. But again, as an overview, as you know, we work with 2D data. I mean, it could be 3D as well, but you were talking about 2D and geotechnical data, which is on-point information of the situation. This is basically what I've shown now is a continuation of what we have published last year, also together with Pedram. And there's a publication on that as well, so you can have a look on the different prediction methods we have tested. But we started with actually comparing different predictions of CPTs to make a basis for a lot of discussions going on, which method to be used for creating interpolated or synthetic CPTs, where we have tested distance weight based methods. So I'm talking about inverse distance weighting, but also kriging, but also we have incorporated machine learning, which I'm not going to talk about today. For seismic data, this is where it gets interesting. There are different ways of incorporating seismic data. We also did that, but we are focused on post-ex seismic attributes, as you can see later. And this is just a reminder of the situation we have. This is actually a nice example from the German North Sea, and then a rare example where we have a lot of ground truth data. So here you can see boreholes or CPT locations. This is being used for the ground models, as you can see, but we're now talking actually about the picture below. So what we want to create is an area-wide information of the geotechnical data. And we can only use or create that basically by predicting or interpolating in between, as you might know. But this gives you a nice picture here, for example. Here you can see from the geological interpretation a tunnel valley, and you can see that this is related to a very low cone resistance, because this is basically more or less a clay tunnel. I mean, this based on clay deposits, more or less. And yeah, so this concept is what you're also aware of, I think, is spline testing, right? So we create or predict CPT profiles on known locations where we where we know the CPT measure, but we leave it out for the prediction and then compare it later. And in our case, this is the predictions again, since we're talking about rigging or simulation, we are talking about variogram-based prediction in this case. Another overview, basically showing the different methods, so inverse distance weighting, rigging, co-rigging, and simulation. The difference here, and this was also what we wanted to investigate, is actually, in this case, we only have the CPT information. In those two cases, we incorporate also seismic attribute for the prediction, which is something the industry also basically wants. What we do is, in terms of modeling, let's say we predict within the stratigraphic units. So we are dividing basically the different units before we're doing anything further to not mix up things which don't belong together. For example, this clay tunnel valley has nothing to do with the surrounding deposition, of course. We consider the vertical and horizontal direction separately. I think that also makes sense, because we normally have a quite homogeneous, or well, horizontally we have a quite good spatial continuity, whereas vertically, as you see on this small example, we have a lot of changes, and so this is why we consider this differently. And what we also do is we predict the whole thing in the flattened space. So we did the unfolding, which is also part of Isatis, and did the prediction in this flattened space, and then back transforms the data, which is very nice because it gives you, at the end of the day, this nice geological structures back. This is just a concept of the simulation. You're aware of that, probably, that we have different realizations, which we can then stack up to get a best estimate, but also a mean or probability density function at the end of the day, which is then in turn also, again, interesting for our probabilistic ground models. This is now the case study, also from the paper I told you about. It's a small, nice study, I would say. So we have just one 2D ultra high resolution seismic line, and we have 8 CPTs on top of that line. So we have a cluster of different CPTs here, and along the line, different other CPTs, as you see. In this study, one CPT profile was considered as a blind profile. So we have taken that out and compared that again to the prediction. Later in the continuation of this work, which will be hopefully also published soon, we have also done blind tests for all the different CPTs. Here you can see the seismic line. It's a quite simple interpretation. So we have basically 3 units here. This is marine seismic data. You have kind of a clay unit here. The rest is, I don't know, sandish material, more or less. But what we've created here as well is acoustic impedance from the data. And here you can see nicely the clay unit again. So this is the low impedance unit here. And the acoustic impedance becomes important because we use this for the co-approach, for the co-rigging and the simulation, co-simulation, to support the prediction between the CPT locations. Otherwise, it would only be the CPT and the unit separation here. And yeah, you can see some results. This is a direct comparison of the different methods. You can see this is CPT only. This is CPT plus seismic attribute. We have here the best estimate being displayed as a cone resistance, or the corrected cone resistance. And here we have a standard deviation. We see here simply the inverse distance weight-based method, weighting method, which doesn't have naturally standard deviation, and rigging, co-rigging, and simulation. The direct comparison of the standard deviation is, of course, not quite correct, let's say, because it has a bit of a different nature, but we wanted to illustrate it still here anyway, to have an impression for the reader on how it could look like. And what was interesting, that all different methods performed quite well, actually, in my opinion. Of course, here it's a bit blurry for the inverse distance weighting, but it becomes quite sharp for krigging. The incorporation of the seismic attributes did bring some improvements also on the prediction. So it became evident here, for example, you can see that here or here in the simulation as well, that suddenly also really the seismic data is being considered. So this peak here basically corresponds to this high impedance here. So this is really being taken into account, which is nice. It becomes a bit more, how to say, dynamic, I would say, the picture, but this is anyway, as you know, over smoothed result. The standard deviation, as you can see here, we have different one for the different units because we have considered them differently also in the variogram model building. And we have increasing uncertainty with increasing distance to the known locations, the CPT location, which is also clear, I think. And the picture becomes very dynamic in the simulation nature, but again, not to be compared directly. But what we did, we went further now, actually, not only comparing the different methods, but also, again, having a look on how that looks in the design process. For that, we used the simulation, which gives us, again, basically, also the probability density function at every point of the profile. And here you can see now blind test example of just two different blind tests. So CPT2 was here and 4 is here. In black, you see the measured CPTs, and in blue, in this case, you see the best estimate predicted CPT, and then you see the standard deviation range. In the paper we will submit hopefully soon. We have worked a lot on the uncertainty range now because the standard deviation is quite high, but we were able to reduce it. But that is a result I cannot really show right now, but maybe later. But you see, kind of, it has a quite good fit, I would say. And from my experience, I would say that it was the uncertainty range. You cover most of the areas where we are apart from the true measures. But of course, you still have some areas where it doesn't really fit. And how to deal with those areas, we are also currently investigating what effect that has on the design process. But this is all the basis for everything which follows later. This is just a summary of the findings of the prediction methods. It's very general. I mean, that every method performs well and such things. I don't want to talk about that in detail now, but rather move on. So here you can see now what we have done afterwards. So this is the main question, actually, which is also of interest for the industry. Can the predicted CPT be used in the design process of offshore wind farm foundation? Because the problem is, of course, the current regulation says you need to perform or need to retrieve another CPT if you have a monopile location or sorry, a foundation location, which is of course very costly. And the question is now, can we use the predicted CPTs equivalently to reduce site investigation costs and times? Because what happens sometimes in offshore wind farm development, you are quite sure with your design, you know where to place the turbines, and then suddenly the whole design changes or the layout changes because of some factors, and then it's for the developers very costly. Anyway, but here we did something else in this study, basically because the uncertainty range, as I said before, was quite high for the simulation. What we did, we compared, or we merged actually the different uncertainties or the different prediction methods we have used, and came up with an uncertainty from that. That doesn't need to bother you right now, but just that you understand that this looks a bit different. Then this was basically mainly done by our partners from GOD here. We made some assumptions on the design of a monopile foundation. We used the predicted QT and FS, so the cone resistance and the sleeve friction from the CPTs. Pore pressure was assumed because the results were not very good, but this is also completely fine. A low case for the pi was also assumed, basically, somehow how much load is acting on the turbine and what dimensions they have initially. this is necessary to come up with a kind of a beginning, starting point. And yeah, anyway, so this is the pile as it is for the test study. It has a diameter of 6 meters. So here you know also what we're talking about. And offshore wind farm development, 6 meters, that's quite a lot. It goes up to 10 to 12 meters also for very large monopiles. So this is really a huge structure at the end of the day. Some things about wall thickness and loads, you don't need to really care about that here. Here I just wanted to highlight basically that depending on where we are in the soil profile here, we of course have a kind of different PDF when we're talking about the probability density function here. So here we have a broader one, and here we have a narrow one. This is interesting because in the design process of the monopile foundation, we're now talking about also probabilistic design in 2 or 3 slides later. But now what the engineers do is actually what you can see here, without going too much into detail, but what you can see here is the pile length. So the length of the pile, this one here. And here you can see the pile head displacement, which is the displacement at the head of the pile if you would push against it, basically with a given force. And what they use for the design is a design pile length, which is then here, which is 10% of the minimal pile head displacement, which is here. This is kind of a design requirement from the engineers. Don't ask me further about that, please. But this is where we go with. And when we're looking at it deterministically, we have some results here. So we started with a deterministic view on the whole thing with a mean of the predicted profile. And this was very interesting to see for me, at least because we see here for the different locations of the CPTs, we see the design, so the length of the monopile for the true measured CPTs compared to the predicted CPTs. And you see that there's not much difference actually in length of the pile. So I put it into percentage here as well. This was interesting because that would indicate that this works quite well. And when you would put a kind of an uncertainty buffer on top of it, you cover quite well the true measured CPT. As you can see here, there's still differences of half a meter. This is important, of course, still because I mean, the monopiles are made of steel, and steel is very expensive. And you have seen that we are talking about huge structures. So we're talking about a lot of money at the end of the day. And if we can prove methods which work well, and also very confident we can save actually money on 2 sides, on the site investigation, but also maybe on the amount of steel we need. Or the other way around, maybe putting on more steel on the turbine is, I don't know, might be cheaper than doing another site investigation. So whatever the designers or developers want to do with that, they can just, maybe even decide for themselves. But next step is basically now the probabilistic design. So you can see basically the same as this one here. This is just for one example here for the best estimate, this curve here. But we can do this also in a probabilistic manner. And we do that by picking from the CPT profile. I mean, there are different ways to do that. We're also testing both of them right now, different possible profiles, basically, which lie within the uncertainty range of this, what you can see here. And then you come out with a lot of different of those curves, and each of them has, of course, a bit of a different design length, right? And which will give us, in turn, what you can see here now, a kind of a distribution of the design pile lengths for a given CPT location. And you can see 2 examples here, CPT 1 and 4. You can see the distribution of the probabilistic design. And then here in this case, what was decided to take the 95% quantile as a design pile length, which is then somewhere here. So most of the cases which have a shorter length, which is less stable, let's maybe put it like that, are being then avoided, but we're going for the safe side. There's just some cases where from the probabilistic design that pile lengths would be longer. But this is where we go with. So this is acceptable in terms of risk, let's say it like that. And you can see the direct comparison of the lengths here. What is interesting, you are always longer, which is not bad because you're safer, right? So you have less risk of maybe failure over time. And I think this is also an acceptable way for CPT 1 to 4, whereas CPT 5 and 6 here we can a bit discuss if 50% more, because we're talking about 4 meters, it's a lot, is acceptable or not. What we can say from the data, this increase might come up with the relatively high uncertainties which were encountered here in CPT 5 and 6, which can be also a problem of the prediction itself. Yeah, so this is, I think, a very nice study and very relevant for offshore wind farm development right now. And yeah, just a conclusion, outlook, a short one actually. As you have seen, we can apply geostatistics in various ways actually in offshore wind farm development or ground modeling. I have not even covered all of that. So there are much more studies going around, not going into the direction of predicted CPTs, but also, yeah, I think there's a lot. If you're interested, just search for that. So in the future, we will focus more on optimization of workflows. I put this in here kind of because we are actually encountering calculation issues now, since the offshore wind farm areas are quite large and we want to have a very high resolution, specifically vertically. And so we need to find ways on how to improve that, because otherwise, yeah, we might run into calculation issues here. We will work on a full probabilistic ground model. This is part of a research project, which is also written here, proper model. So we will work further with a probabilistic ground model, also incorporating the CPTs to have also the CPT uncertainties in there. We haven't managed to go that far already, although Petram already have built up a basis for that. And we might look into the channel probabilities in 3D. This was a good feedback from my PhD supervisor, actually, to not only look at it in 2 dimensions, but also the vertical dimension, because you have seen that the channels, they pinch out at some point, and we want to see really kind of put this into a risk map at the end of the day, because if you have a lot of clay, for example, it's just talking about an example here, it is more like a geohazard than just having a counter, having like 10 centimeters of channels. And this is something we can map out and put into a probabilistic manner when we look at it in 3D. Yeah, and there are 2 journal papers then hopefully coming out soon. So hope you can read that in the future. So the one has been submitted, as I said, and the other one is submitted soon, and both is based on what I've just presented to you guys. And that's it from my side.